Hello guys, good morning or good afternoon. My name is Aymar Mark Gabal, BSCB 3A. My topic is design a control system. Next. Chapter 1. History of control system. Role of a computer engineer. Definition of a control system. Configuration of a control system. Analysis and design objectives. The basic steps in the design of a control system. The fundamentals of block diagrams. History of control systems. Control systems existed way back before humanity exists. Numerous biological control systems existed in all the living things of this planet. When humanity came, they developed another type of control system, a mechanical control system. The table shows how the technology and control system evolved. 1600s, incubator. Next is 1700s, fly ball governor. 1800s, stability analysis of governor, route governor. 1910, autopilot. 1920s, feedback amplifier. 1930, night quiet stability frequency response tools. 1940, optimal filtering sample data systems, root locus. 1950, maximum principle dynamic programming numerical optimization. 1960, Apollo digital autopilot aircraft stability augmentation. LQG design internal navigation microprocessor. 1970, feedback control of automotive engines, aircraft auto landing. 1980, computer-aided control design, internal model control. 1990, GPS, unmanned aircraft, high-precision disk drive control. 2000, automotive stability augmentation systems, farm tractor, auto steering via GPS. 2010, driverless car. In the present is unknown. Role of a computer engineer. What did you observe from the table above? The first recorded mechanical control system was in 1600s. Mechanical control systems continued to evolve until 1800s. In the early 1900s, electronics were added to the mechanical control systems. It continued to evolve until mid-1900s in 1960. Computerized control systems started. The difference of a mechanical control system and a computerized one. A computerized control system is a lot better than electromechanical or pure mechanical control systems. Hence, as a computer engineer, it is your job to computerize every mechanical or electronic control system to improve their performance and thus simplifying our lives. Are you willing to face the challenge? If yes, then condition your mind and body to harvest every information that this course will give you. Widen your imagination and develop your creativity, and maybe you will be the next in line in the advancement of control system. What is a control system? A control system is an integration of different devices or subsystems assembled to produce a desired output with desired performance, given a specific input. A system can be manually controlled or automatic. Manual control means that it involves human intervention to control the behavior or the output of a certain system or machine. An automatic control system is a system that responds differently to different situations to achieve the same expected output even with different inputs and some disturbance. Configuration of a control system. There are two major configurations of a control system: open loop system and closed loop. A closed loop system and open loop system. A closed loop system is exactly the same with the open loop system except that it has a feedback part. The sensor or the feedback enables the system to adjust to input differences, and disturbance, thus providing the same expected output. How? The closed-loop system compensates for input variation and disturbance by obtaining information from the output. Analysis and design of a control system. As what it is mentioned in the first part of this module, one of the focus of this course is to enable students to analyze and design a control system. As an engineer, we should have knowledge and understanding on how to analyze an existing system or to design a new one. Analysis is the method to determine how the system works. Design is the method by which the function of the system is created or varied when we are analyzing or designing a system. There are few things that we need to know. These are the transient response, steady state response, stability, hardware specifications, cost. So, the transient response. When you pull the accelerator of motorcycle, the engine will respond and the motorcycle moves forward. The change of speed of the motorcycle or the acceleration is dependent on how you will pull the accelerator. Of course, if you are the driver, you will speed up to pace comfortable for you. Next, the steady state response. Steady state response is the response of the system which does not approach zero. For example, in an elevator, it should always stop in a way that is exactly leveled on the floor. In a coffee dispenser, the time the water pours in the cup must be just right. If it is too long, the cup will overflow. If it is too short, it will not fill the cup fully and the user will complain. Here, the focus is accuracy. Stability. In life, stability is important. All of us want to have a stable financial situation, a stable relationship, a stable job, and a stable place to stay. It is the same with control systems. It should be stable for it to be beneficial. Stability is one of the important characteristics of a system. When you turn an electric fan by pressing the number 1 button, the fan will start to turn. It will have a speed that is set for number 1. Its speed remains to be the same no matter how long it is turned on. Its speed is constant and is not affected by the change in temperature, loud noises, or any disturbances. That stability, its operation, and functionally does not decay. Hardware specification. In designing a system, the specification of hardware used are also considered. If you want to design a water pump, you must consider how strong your pump will be when pumping water, how fast it will consume gasoline or electricity, or what is its size and construction. Does it fit in a place you intended to put it? Can it sustain the environmental condition where you want it to be deployed? So next is cost. This must be considered in every system design. No matter how good your designed cell phone is, if it costs 1 million pesos, no one will buy it. So next is, here are the steps how to design a control system. Step 1. Make a physical design based on the requirements. Next step is, create a functional block diagram. Next, draw a schematic diagram. Develop a mathematical model. Simplify your design. Analyze and design. So step 1. Make a physical design based on the requirements. Let's say we want to design a system that will monitor your dog's whereabouts. The requirement is the system must tell you where your dog is in real-time basis. Wherever you are, it must inform you your dog's location whenever you want to know its current location. So the physical design must be something that the dog can comfortably wear. It should be battery powered, it should be water resistant and tough enough that it can be destroyed by your dog. These are just the few things the system must have. We need to identify all the necessary features the system requires and check the market for the necessary hardware availability. Step 2. Create a functional block diagram. Design a very simple block diagram of the operation of your system. Does it need a transducer, a controller? What other components it should have? Does it require a feedback system? Separate each function to each block. Step 3. Draw a schematic diagram. It should be that each block can be represented by a schematic diagram. Here we will identify the mechanical part, the electronic part, and the computerized or the programmable part. Any. Take note that in making the first schematic design, ignore the possible external disturbances or else it will be too hard for us to design one. Once the design is done and theoretically operational in an ideal environment, start adding the possible disturbances one by one. Make adjustments on your schematic based on these disturbances. Step 4. Develop a mathematical model. This is the hard part, but this is the one that differentiates you from others. Many can design a system without knowing the concept and theories behind. They do it using trial and error. We, as engineers should design system based on laws of science and mathematical equation, not by trial and error. If you will someday design a flying car, it should not be done by trial and error. This will be discussed in details in the next chapter. Simplify your design. Try to reduce the block diagram if possible. We will discuss the reduction of block diagram in the later chapters. Step 6. Analyze and design. When everything is set, we can begin in the analysis and design of the system. In this step, we will test our system if it meets the required performance and function. Don't forget to test its transient response, steady state response, and stability. Diagram fundamentals. A block diagram is a graphical representation of a cause and effect relationship between the input and the output of a physical system. As what its name implies, it is composed of rectangular blocks where each block has its own function. The blocks are connected with arrows and the flow operation is from left to right. Common parts of a control system block diagram. Input transducer, controller, plant or process, feedback. Transducer. An input transducer or input filter is responsible for converting the input signal into a form that the controller can interpret and use to drive the plant. In an audio system, your microphone might be your input transducer. The input is an external sound or human voice and is converted to electrical signals for further processing. Controller. The controller provides the desired control signal to the plant. The plant's operation is dependent on the controller. It is also responsible for computing the difference between the reference signal, the input signal, and the output signal, feedback signal. The result of this computation will be used to adjust the process to maintain its output signal. Or process. As mentioned earlier, the plant is responsible for the main function of the system. In the case of the audio system, it could be the amplifier and the speaker. The amplifier amplifies the weak signal while the speaker converts the electrical signal to its original form. Feedback. In the case of an air conditioning unit, ACU, the thermostat or the sensor that measures the room temperature is the feedback of the system. The feedback enables the ACU to remain the temperature the user set regardless of the outside temperature variation and the number of people inside the room. The feedback makes it possible to have a cruise control in a car, an auto landing in a plane, and to maintain the satellite elevation in the atmosphere. A feedback is a sensor, so it should have accurate measurement and sensitive to noise, reliable, and must have a linear behavior. In other words, it must be stable, tracks a desired input, ignores disturbance, and can work in varying environmental conditions.